This is eventually going to be a lecture over section 3.2. I feel I should just review a few things from 3.1 just because that video was kind of long. So I'll make a few problems up. They're not in the handout, but there are all sorts of things that should be doable. So for the first review problem, should be able to find the x and y intercepts if I give you an equation. And I'll write and sketch a graph. I'll make it just a reasonably easy problem. How about 3x minus 6y equals to 12? Be nice if you pause the video, worked out the problem, and then checked your answer. But if you don't remember how to do it and you just want to watch, it's okay. So I'm going to find the intercepts first. The first intercept I'm going to find is the x-intercept. I find x-intercepts by plugging in 0 for y. So doing that computation, the 6 times 0 turns into a 0, which makes the left side simplify to be 3x. And I'll just divide both sides by 3 and get x equal to 4. And I'm going to write my x-intercept as a point. So in for my answer, for the x-intercept, I'm going to write it as a point x equal to 4, y equal to 0. I'm going to try to squeeze in the y-intercept so I can get the graph on this page. So right next to the x-intercept, I'm going to compute the y-intercept. You find the y-intercept by plugging 0 in for x and solving for y. So I get 3 times 0 minus 6y equal to 12. The 3 times 0 turns into a 0, which leaves me with minus 6y equals to 12. I'll divide both sides by a minus 6. And I'll get y equal to negative 2. And then again, in my answer, I'm going to write a nice y-intercept, write it as a point because it's a point on a graph, and all points on the graphs that we do have both an x and a y coordinate. And I'm going to write that as the point 0, negative 2. I don't need to use graph paper to sketch a graph, so I'll do the sketch a graph in the little area that I have left. And it can be really crude. I'm just going to make a little Cartesian coordinate system. I have an x-axis and a y-axis. I'm going to make 4 little tick marks on the x-axis and just 2 tick marks on the bottom of the y-axis. I'm going to plot the intercepts. Here's the x-intercept of 4, 0. Here's the y-intercept of 0, negative 2. And to do a graph, I just connect those points with a line. It's nice if you put arrows at the end of the line just to signify that it doesn't stop, but it's okay if you don't do the arrows. I don't know how to make my computer do the arrows, so when graphs aren't supposed to stop, when I draw them on a computer, you won't see the arrows anyways. But it's nice to have if you can draw them in. So that's one style of problem that you should definitely be able to do from section 3.1. The second style of problem that you should be able to do from 3.1 is this style of problem. The instructions might say write in slope-intercept form. Then identify the slope, the y-intercept. I'll even make it harder, sketch a graph. In the section, we didn't do the sketch a graph part, but the sketch a graph is hardly that hard. And I'll make a hard problem up, because sometimes on the test, this style of problem I load up with fractions. So how about this? 1/3 x minus 1/4 y equals to, I don't know, 2. I think that'll be okay. Let me make sure. I'm trying to make sure I'm not getting a fraction here. So boom, boom. I think that's going to be fine. I might get a fraction for the slope, but I don't think I'll get a fraction for the y-intercept, which is what I'm really concerned about. So step 1, again, if you can solve this without me, you're doing way better than if you wait for me to solve it. So if you just recently did the homework from section 3.1, so something that was in the homework and something that theoretically can make it onto the test. So step 1 is to do the right in slope-intercept form part of the instruction. And that part of the instruction just tells me to solve it for y. So I could have said, instead of writing right in slope-intercept form, I could have just written solve for y. But I didn't. So I wrote something that is more mathematically elegant, I guess. So to do the first part, I'm going to minus 1/3 x from both sides. And I'll get minus 1/4 y equals minus 1/3 x plus 2. And now I'm going to divide everything by negative 1/4. Or I could multiply by negative 4, because dividing by a fraction is the same as multiplying by the reciprocal. Because my calculator rocks with fractions, I'm just going to divide by negative 1/4. To the left of the equal sign, the negative 1/4 divided by negative 1/4 is 1. To the right of the equal sign, I'm going to pull out my calculator. I think you get 4/3 and negative 8. So first fraction I'm doing is fraction over a fraction. So I'll do a fraction here and do negative 1/3 over, then another fraction, negative 1/4. So that looks quite a bit like negative 1/3 over negative 1/4. Not that you could see that so well. And my calculator tells me that that's positive 4/3. I feel good about that. The two negatives should definitely cancel out to be a positive. And if I multiplied by negative 4, I would have gotten 4/3 easier. Second, I'm going to divide 2 divided by negative 1/4. And I get negative 8. Again, dividing by negative 1/4 is the same as multiplying by negative 4. And I feel good about that. So here I could write plus negative 8 and put the negative 8 in the parentheses. Or I can write y equals 4/3 x minus 8. So this is the first part. This is considered writing in slope-intercept form. And I'm basically done with everything that's hard. The rest of what needs to be done is not going to require any algebra. The next thing it says is to identify the y-intercept. So I'm going to write down the word y-intercept, and next to it I'm going to write what the y-intercept is. The y-intercept is the non-zero part of the y-intercept is the number after the minus sign, or this negative 8 up here. And we usually write it as a point, so I'm writing it as a point 0, negative 8. The slope, probably should have done that first, but it doesn't matter. The slope is a number in front of the x without the x, and that's 4/3. And I'll sketch a graph, but I think on the test I won't ask you to sketch a graph for this problem. So to sketch a graph, it's easy. I have graph paper again today. I'm going to plot the y-intercept, which is a point 0, negative 8. So this is the sketch a graph part of that problem I just made up. And then the slope, being 4/3, tells me I should go up 4 and right 3. So from here I go up 1, 2, 3, 4, right 1, 2, 3, up 1, 2, 3, 4, right 1, 2, 3, up 1, 2, 3, 4, right 1, 2, 3. All of those points are going to be on the same line. Probably be nice if I pulled a ruler out, but I didn't. And that would be a completely adequate graph for that particular problem. So both of those things are test worthy from the last section, section 3.1. There's more that's test worthy from 3.1, so I'll dig out some more paper, because I guess I still have some more. I'll do another 2 more problems. And that's about everything that's test worthy. Oh, there might be something I'm forgetting, but most of the test worthy stuff. So the next thing I'm going to do is find the equation of the line in slope-intercept form, is y equals mx plus b form, with slope 3 and passing through the point 1, 7. So this was at the end of section 3.1, and the video was so long you might have not actually got to this. So if you didn't get to this, you're seeing it now. My answer needs to be something in the form y equals mx plus b, but I need to change the m and the b to numbers that fit the problem. The m stands for the slope, and I've given the slope. So in my answer, in the y equals mx plus b equation, I'm going to change the m to 3. The b isn't 7, because b comes from a point that's 0 comma some number. I have to do algebra to solve for the b. The algebra that I'm going to do to solve for the b is I'm going to take the numbers that I see, m equal to 3, x equal to 1, y equal to 7, and plug them into the equation y equals mx plus b. Solve that, and that will give me the b for my equation. So I'm going to go 7 equals 3 times 1 plus b. That's going to give me 7 equals 3 plus b. I'm going to minus 3 from both sides, and I'll get 4 equal to b. In my answer, in place of the b, I'm going to put a positive 4. So one more problem I want to do, it's going to be similar in instructions to this. Find the equation of a line in slope-intercept form, but instead of giving you a point and a slope, I'm going to give you 2 points. So last review problem. These still have not got to the new stuff yet. So still review of section 3.1. And when I randomly make up review problems, they are all potentially test worthy. I'm not going to make up something that I know will never be on a test that I give. So same instructions, more or less. Find the slope intercept form of a line that passes through the points 2, 3, and 5, 15. So in order to do this problem, just like in the last problem, I'm going to start with the equation y equals mx plus b and change both the m and the b with numbers that fit the problem. In the last problem, because I gave you the slope, you had the m. I didn't have any points that had 0 for an x, so I didn't give you the b, and I had to compute the b. In this problem, I don't have the b because I don't have a point that has an x equal to 0, nor do I have the m, so I have to compute both. You have to do m first. So first I'm going to find the m by using the slope formula. Take the y-coordinate of the second point, which is 15, minus the y-coordinate of the first point, which is 3, divided by the x-coordinate of the second point, minus the x-coordinate of the first point. And when I do that, I get 12 over 3, which is 4. So in my answer, in place of the m, I'm going to plug a 4. Next thing I need to do is find the b, and you have flexibility. You have to use the equation y equals mx plus b to find the b, but you could use m equal to 4, x equal to 2, y equal to 3, or you could use m equal to 4, x equal to 5, y equal to 15. Doesn't matter which point you use, as long as you group the x's and y's together. So I'll show you that both of them give you the same b. This one, if I go 3 equals 4 times 2 plus b, this would give me 3 equals 8 plus b. I'd minus 8 from both sides. and I'll get -5 equals b. This version, I'd go y15 equals m4 times x5 plus b. Gives me 15 equals 20 plus b. And when I minus 20 from both sides, I get -5 equals b. That -5 needs to go in my answer, and I have a flexibility. I can write like that, or for an answer, I can write 4x minus 5. Both of these are considered slope-intercept form. That line, if I graphed it, it's going to pass through the points 2, 3, and 5, 15. And, well, that's all I needed to do. Okay, so that's a quick review of section 3.1. 3.2 is a short, friendly section. I don't think there's enough problems in 3.1, so I'm going to make up a lot of extra problems while I'm doing the section, because there just isn't, like I said, I don't think there's enough problems, and I don't want to do all of your homework problems, so I'm going to make some up. The first 4 problems in section 3.2 aren't super important, nor are they on the test, but they're not hard, so I'll do them real quickly. The first thing I see is a new word. Talks about relation, and a relation is just a group of points. Usually with the x values first and the y values second, but not always. So I'll say a group of points with the x value first and the y value second. So from this table in problem 2, if I wanted to list all the ordered pairs is the same as points. So the instructions in this problem say take each relation. I'm given a relation. It's in a table. I want to write it as a set, or another word for set is a group. So I use very mathematically elegant words in my instructions. But I'm supposed to take this relation that's given in a table and write it as a group of points with x's in first and y second. And it's real easy to do. This is the relation written as ordered pairs or points. A gets paired with W because A in the x column gets paired with the W column, the W in the y column. B gets paired with x, C gets paired with y, and D gets paired with Z. So those are the points or the ordered pairs that are implied by that table or that relation. That's only 1/3 of the stuff I have to do for problem 2. The second thing I do, it says list the domain. And in a relation, the domain of a relation I need to know what it is before I can write down what to list it. Domain of a relation is all the x coordinates of the points in the relation. So for of the 3 things that I needed to do for problem 2, first I needed to write the relation as a set of ordered pairs. Second, I'm asked to find the domain. The domain is just the A, B, C, and D. If I want to be mathematically elegant with my answer, I would put some sort of grouping brackets to enclose those letters together. And the brackets that we usually use are these little, they're called set braces. And when a relation just has a finite number of points, in this case 4 is a finite number, we usually, when we write the domain, we encapsulate the elements or the letters or numbers in the set with set braces. It's not such a big deal if you don't have it. The last part of this, I'm supposed to write the range of this relation. And in order to write the range of the relation, you need to know what the range of a relation is. I'll scribble it in here. The range of a relation is all of the y-coordinates of the points in the relation. So for problem 2, if I wanted to write the range of this, I'd look at the 4 points. The y's are w, x, y, and z. So it would be correct to say the range of this relation are the letters w, x, y, and z. If you didn't put any grouping symbols around those letters, it's not wrong, but I'm sure in any math book you'd pick up, they'd have the set braces grouping those letters. So there's no algebra to do for that problem, nor is there any algebra to do for, I think, any problem in section 3.2. So it gets to be unforgiving in terms of partial credit, this section, but it goes really fast once you know what the questions are asking you to do. So problem 4, because it's in this grouping, is going to have me do the same 3 things. Write the relation as a set of ordered pairs, list the domain, and list the range. The difference between problem 2 and problem 4 is the x's and y's are going up and down as opposed to left and right. So the first thing I'm going to do is I'm going to list the relation as a set of ordered pairs. So I'm just going to make points up. And I'm going to pair each x with the y above it. So I'm going to compare these like this because that's x, y. So it's going to be 1, 1, 1, 2, 5, 4, 9, 2, and 8, 1. I didn't probably enclose the relation and set braces in the last problem. I probably should have. Because it is a set, I should have probably put it in these set braces. Yeah, it's not the biggest deal if you forget to do that. It's not really that important. It's just kind of more mathematically elegant. If you were a math major in a high enough math class, a teacher would think that's a big deal, but it's not such a big deal in our class. Next thing I want to do is make the domain of the relation. So I'm just going to take the x values, which are 1, 1, 5, 9, and 8. This would be a correct domain, but an inefficiently and not nicely written domain. This is okay, but not the best answer. Normally, if I'm going to write the domain of a relation that only has 5 points, I'm going to write the numbers if they're numbers in ascending order, and I'm not going to duplicate if there's a duplicate number. A better answer for the domain of this relation wouldn't have the 1 written twice, and would take the time to write the numbers in ascending order. But it's not wrong what I initially wrote, it's just not a slick answer. And the last thing I want to do is find the range. And I'm using set braces again, and the ranges are the y's, so I'm going to write 1, 2, 4, 2, 1. The y coordinate of every single point belongs in the range. And similarly, this is an okay answer. It's not necessary to duplicate points, so a better answer would just have the numbers 1, 2, and 4. But I'd live with either answer. This is the easiest part of the section. The next part of the section, for the most part, it's easy once you kind of catch on. However, if you don't pay close attention, you can blow these problems on the test. And if you blow these problems on the test, it'll do horrors because there's not a lot of partial credit. So the rest of the problems, or at least the problems between 5 and 14, give me a picture on a graph of a relation, and the points are listed here, so I don't have to list the points that make up the relation, but I'm asked to write the domain in the range, and so I'll just do that. So for this number 6 in section 3.2, I see all the points of the relation, and the x-coordinates are -3, 1, 1, and +3. Again, this is an okay answer, but it would be better to say the domain is just -3, 1, and 3. So the domain, when the relation has a finite number of points, this relation has 4 points, it's just the x-coordinates of each of the points. The range is going to be the y-coordinates. So I'm going to write -2, -3, +2, and +4 for my range. That's not in ascending order, doesn't bug me, but if you want to, it's probably better if you go from small to large. -3 is the smallest number, -2 is the second smallest, and then 2 and 4. But if you don't take the time to rearrange it, it's wouldn't lose a single point by doing that at all. So I'm going to make up 2 more problems like number 6, not in the handout, before I get to the other problems, which are completely different in terms of they don't connect to the beginning problems quite as nicely. So this is just an extra problem, not in the handout. And I'll say find the domain and the range. And again, this is just not from the handout. This is just, I'm completely making it up because I didn't think there was enough of these styles of problems. So I made this relation have 1, 2, 3, 4, 5 points. Super easy to write the domain and the range, especially if you're not over concerned about writing a number twice or writing things in ascending order, which you don't really have to be concerned about. So for this relation, the domain has the x values of -5, -1, 0, 5, and 8. I can't really write it in a better order than that. There's no duplication there. I wrote the numbers from smallest to largest, so that's a really nice answer. For the range, I'm going to pick off the y's. Here's a -3. Here's a 7. Here's a 2. Here's a 1. And there's a -3. That's okay. What it has that makes it not great is it has the -3 written twice, which I really don't have to do, and it's not written from smallest to largest. A better answer for the range would be writing -3, 1, 2, and 7. But as long as you have the y values from all the points, it's not a deal breaker if you don't have a nice order or if you write a number more than once. So there's a lot of forgiveness here. Those are the easy problems, so I won't do another one of those. The difference between every problem that I've done so far and the next problems are the style of relations. Problem 6 and the problem I just made up, they're an example of finite relations. Finite meaning I can count the number of points. The relation in number 6 was composed of just 4 points. And when you have a finite relation, the domains and the ranges are written with writing each individual x and each individual y, and you use a nice set notation. This is also a finite relation. It has 5 points as opposed to 4 points. Even if I had 100 points, I can use this strategy for writing the domain and the range. The rest of the problems in this section are called infinite relations, meaning they have more points, they have infinitely many points. So this problem 8 is an example. This is an infinite relation. And even though I have 3 points drawn, there are definitely more than 3 points on this graph. Specifically, here's a point that's not drawn or not marked, but it's a point on the graph. I believe that's about the point 0.05, but I could be a little bit off. So if I was to write the domain using set notation, it would be wrong to say the domain are the values -5, -3, and 0. The difference between the last problems and this problems, the last problems the points weren't connected. It's not correct to connect the points. You have to leave them how they're given. You can't just connect them and change the problem. But in this problem, it's impossible for me to list all the points. Here's maybe the point -1, 0. So if I had just written that for the domain, I'm missing that -1. As a matter of fact, any place where I could make a dot, I'm going to have an x value that belongs in the domain. And the unfortunate thing is, this is an infinite relation, which means I could make infinitely many dots if I had a smaller pen. So every place I'm making a dot, there's a point, and its x value would need to be part of the domain. So I've written about 40 points. So if you can find the x value of each one of those points, you could start to list the x values of some of the points of the relation, but I still haven't gotten all the points. I haven't drawn, there's more points that I can draw. So this is an infinite relation because any place where the graph is connected, there's infinitely many points, and it would be wrong to write the domain listing all the x values. What you have to do for the infinite relation is describe a range or an interval of values that x's can take. So to find the domain of an infinite relation, it's not hard, meaning it has more than just a fixed number of points. You have to identify the far left points and the far right point. So I'm going to look at this graph, and I should have been kind enough. You need to identify the point that's most left and the point that's most right. As I look at this graph, this is the left side, this is the right side. This point right here, I would consider this of the graph. It's the left edge of the graph, so I would consider this the most left point. And then if I go off to the right, this point right here, I would consider the most right point of the graph. There are definitely other points that make up this graph, but in terms of writing a domain of an infinite relation, if you can identify the most left point and the most right point, then you can write the domain in a nice format. So this is not the correct domain because there are more than 3 points on this graph. So I have to resort to writing intervals. And in this problem, where you have an infinite graph and the endpoints are part of the graph, to write the domain down, you write square brackets as opposed to the squiggly set brackets. The first number I write is the x coordinate of the most left point. So here I'm going to write the x coordinate of the most left point. And the most left point is the point -5, 0. Its x coordinate is -5. And then I'm going to write the x coordinate of the most right point. The most right point is the point 112. Its x-coordinate is 1. So for this problem, the domain is not the numbers -5, 3, 0. It's the interval from -5 to 1. And what that tells somebody that reads mathematics is if you give me a number between -5 and 1, I could find a point on the graph that has that as its x-coordinate. To do the range, to find the range of an infinite relation, of which this isn't infinite, because as the points are connected, once the points are connected with any curve, it's an infinite relation as opposed to a finite. You need to identify the bottom and top points. In terms of a graph, the top is at the top of the y-axis, the bottom is at the bottom of the y-axis. I need to find the points closest to the top and closest to the bottom. This point, -3, -4, for this graph, it's the bottom point. There's no point lower than that. And the point 112, it's also the top point. It's both a right and a top. The point -5, 0, it's at the far left end, but it's not the bottom. To do the range of an infinite graph, I'm also going to make square brackets, comma, square brackets, and I'm going to pick off the y-coordinate first of the bottom point, and then I'm going to write the y-coordinate of the top point. So if I have the top and the bottom points identified, it's easy for an infinite relation, a relation that the points are connected, to find the domain and the range. So the range, I need the y-coordinate of the bottom point and the y-coordinate of the top point, and I always write top to bottom. So for this problem, the answer to problem 8, the range is -4, 12. I'm going to write a problem down and have you do the domain and range. This is extra, not in the handout. So find the domain and the range. I'm going to label some points, the only points that you're going to need. Here's the point 7, -4. Here's the point 2, 6. And here's the point -1, 2. This is an infinite relation, so when I write the domain and the range, I need to write square brackets in intervals with 2 numbers in each. Again, it would be wrong to say the domain is -1, 2, and 7. That would imply the graph only has 3 points, but it has way more than 3 points. Here's the point 0, 4, so 0 would have to be in this listing. Here's the point 4, 4, so 4 would have to be in this listing. So you can't just take the coordinates of the points that are given and write the domain or the range down when the points are connected with some sort of curve. So for this problem, to find the domain, I have to identify the point that's furthest left and furthest right. This point is at the left edge of the graph. Let's say that's the most left point. This point is at the right edge of the graph. I'm going to call this the most right point. To write the domain of a connected or infinite graph, I take the x-coordinate of the most left point, which is -1, and then I write the x-coordinate of the most right point, which is 7. Range is completely different. Range, I have to identify the bottom and the top point, and I have to take y values. this point here, not only is its furthest right, it's also the bottom point. This point here, it's the top point. So when I go to write the range of this, I take the y-coordinate of the bottom point, which is -4, then the y-coordinate of the top point, which is 6. And that's it. I'm done with that problem. There isn't anything else I could do to make it more correct or less correct. Let me make up a couple more problems. So find the domain and range of this. So if this was a test question and it said find the domain and find the range, again, this is not from the handout. I'm just making up problems because I didn't think there was enough problems in my handout. If this was a test question, the points aren't connected. This is a finite relation. And in finite relations, the domain and the range, you use the squiggly set brackets. And you just write the x and the y coordinate of each point. So the domain for this would have the numbers 1, 2, and 4. That's the x coordinate of the 3 points. The range would have the number -2, 2, and 5. And again, the order's not a deal breaker. There was no duplicate x's or duplicate y's, so I didn't have to worry about that. So it's a big difference when we're finding the domain and range from a picture. If the points are disconnected, like here, they're not connected with any sort of curve, or if they're connected. Make up one more problem before I dig back into the handout. So let's do this. So this is the point 7, 5. I'll label this point, and you have to decide if you need it or not. There's the point 0, 0, and here's the point -5, -4. So when I go to do this made-up problem that's not in the handout, it would be wrong to say the domain is -5, 0, and 7, because the points are connected. There's more points than I've shown. For instance, here's the point right there that has an x of 5. Number 5 would need to be part of the domain. Here's a point that has an x of 4. 4 would have to be part of the domain. It's wrong to write the domain and range for this style of graph, an infinite relation, with the squiggly brackets. So I'll give you a second to try to figure out what the domain and range is. You'll find that that point 0, 0, it's a complete distractor, because it's not the far left edge, it's not the far right edge, it's not the bottom or the top. It's just a point I threw in to mess you up a little bit. So if I'm doing the domain of this, I need the point that's furthest left and its x-coordinate, the point that's furthest right and its x-coordinate, and I'll write those in the domain. So my domain's going to be -5 to 7. Then I need the bottom point and its y, and the top point and its y to write the range. So the range is going to be the y-coordinate of the bottom point, which is -4, the y-coordinate of the top point, which is 5. Okay, I'm going to get back into the handout. There's one little subtlety that comes up, but not quite yet. It comes up on problem 12. Shut that off. It comes up, but it doesn't come up yet. So this is similar to the problem that I just drew. Again, it would be wrong if you said the domain is -1, 0, and 2, because the points are connected. There's more points than just the 3 points that are labeled. Both your domain and your range need to be with just 2 numbers and with intervals. For the domain, I need to find the far left and the far right point and their x-coordinates. Always read left to right and then bottom to top. So for this graph, the x-coordinate of the far left point is -1. The x-coordinate of the far right point is 2. That it'd be proper to say the domain is -1 to 2. And now I'm going to go bottom and top points and find their y's. The bottom point is the point 2, -4. The top point is the point 1, 2. Its y's are -4 and +2. So these would be the correct domains in range. Domain left x, right x, -1 and 2. Range bottom y, top y, -4 and 2. Up until now, either the graph has just contained a finite number of points that weren't connected, and when a graph contains a finite number of points that aren't connected, when you write your domain in range, you get this nice squiggly notation. You write each individual x and each individual y. When the points are connected, we're using intervals. We're finding the most left point and the most right point to find my domain, my bottom and my top point to find the range. If you've noticed every graph that we've done so far that had the points connected, it had solid periods right at the end of each graph, which means the graph ends in right where the last points labeled are labeled. The next graph's a bit different in that one of the edges or the edges of the graph don't have little periods at them, and when the edges of the graph don't have periods, you have to extend the graph. What it really has that I don't know how to draw is arrows. So problem 12, this graph, you'll notice that the edges of the graph don't have periods. I didn't intend the graph to stop. I wanted the graph to keep going forever and ever and ever. And when that happens, I have to extend the graph forever and ever and ever. Of course, I can't do that, so I have to describe where the graph goes. And where this graph is going towards, on the y-axis, the top of the y-axis is a positive y direction. The bottom of the y-axis is a negative y direction. So this graph, in terms of the y direction, it's approaching the bottom of the y-axis, and it's approaching -infinity in the y direction. So because the graph wasn't given nice periods, I need to extend my graph. And then off to the right, the x-axis off to the right goes to +infinity. This half of the graph, it goes down to the bottom of the y-axis, and it keeps going off to the right. It gets down to the bottom quicker than it does off to the far right edge, but eventually, if I let it go down far and far enough, it's going to get all the way to the right edge of the x-axis. So it's going to approach in the x direction. This half of the graph is going to approach +infinity. This half of the graph, it goes to the bottom of the y-axis, so it goes to -infinity on the y-axis, but it goes to the far left edge of the x-axis because it goes down forever and ever and ever, and eventually it gets to -infinity in the y direction, and it gets out to -infinity in the x direction. So any edge of a graph that doesn't have a period on it needs to be extended before I write the domain in the range. And I'm going to emphasize, just in case you can't see this point, it's the point 2, 1. Now that I've extended the graph, I'm going to write the domain in the range by finding the far left and the far right point in its x-coordinate. So this point right there is going to be the most left point. It's further left than any point on the graph. This point right there is the most right point. And to do the domain of any relation that has connected points, I write the x-coordinate of the far left point and the x-coordinate of the far right point. Usually when I'm using interval notations, I use square brackets. It's not technically right to use square bracket on an infinity, because if you use a square bracket, it means the graph actually gets to the end, and it goes forever here without actually getting to the end. It would be more correct to use round brackets, but if you use square brackets, it's just not that big of a deal. So for this graph that needed to be extended, the domain is -infinity, the x-coordinate of the far left point, positive infinity, the x-coordinate of the far right point. For this graph, the points that I've drawn are both bottom points. And this point up here is the top point. When I go to write the range, I want the y-coordinate of the bottom point. There's two bottom points, but they both have a y of negative infinity. And then a comma, and the y-coordinate of the top point, which is 1. That 1 is a solid point on the graph. That y should get a square bracket. The graph really doesn't deserve a square bracket at the infinity. That's the answer to 12. This is the hard part. Let me make a couple up that aren't from the handout just to get you kind of in the groove with these. So let me flip this over and give you this graph. Here's the graph that is a parabola or a U that looks like this. So just like the graph in number 12 that I just did, this is a graph that needs to be extended. You can tell it needs to be extended because I didn't label the points at the edges. I don't know how to make the arrows drawn, but if I don't put dots with points, it means the graph needs to be extended. This edge needs to be extended that way. This needs to go that way. In terms of the y, it's easy. Both of these edges are going to the top of the y-axis. So when I extend the graph, I'm going to say the far left edge is going to the top of the y-axis, which is positive infinity in the y direction. The far right edge is also going to the top of the y-axis, which is positive infinity in the y direction. This half of the graph is going to the far right edge of the x-axis. The far right edge of the x-axis is at positive infinity. This half of the graph, it's going to take a while to get there, but eventually it's going to get to the far left edge of the x-axis, which is negative infinity. So I extended my graphs just like I did the last problem because the edges of the graph weren't marked with a period. Now I'm going to identify the far left and the far right point, the bottom and the top points. This point is the most left on this graph. This point is the most right on this graph. When I go to write the domain, I take the x-coordinate of the most left point and the x-coordinate of the most right point, negative and positive infinity. I'm not going to use these squiggly brackets. That's only when the graph points aren't connected. I'm not going to use square brackets because infinities don't really deserve square brackets because the graph doesn't actually get there. This means it keeps going forever. The round brackets do. And doesn't actually get there. For the range, I need to pick the bottom point and the top points. It turns out that each of these points is equivalently at top. They're kind of at the same level up top, but it doesn't matter in terms of the range. When I go to write the range, the y-coordinate of the bottom point is -3. There's two top points, but they don't conflict each other because they both have the same y value. The y value of the top point is infinity. I should probably square bracket and round bracket. Yeah, we'll do this one. In fact, let's go out of order. Let's do 16 and then 14. So 16 only has 1 point drawn, which means this edge needs to be extended and that edge needs to be extended. Again, it's easy for me to extend the y's, easier for the y's than the x's. This is going to the top of the y-axis, so its extension is going to go to the top of the y-axis, which is positive infinity. This one's going to take a little longer to get there, but it's also eventually going to get to the top of the y-axis. It keeps going up forever. This edge, it's going off to the left edge of the x-axis, which is negative infinity in the x direction. This edge is going all the way off to the right. It's going to positive infinity in the x direction. So because there weren't points labeled at the edges, I extended my graphs, and now I'm going to do the domain. I need the x-coordinate of the far left point and the x-coordinate of the far right point. So the domain here is going to be negative infinity to infinity, round brackets on the infinity, square brackets on the numbers. The range, I need to identify the bottom point and its y coordinate. And these points are kind of equally top. If you considered that the top, it would be fine. If you considered that the top, it wouldn't matter. But this one looks a little bit higher, so I'm going to say it gets higher quicker. So for my range, I'm going to take the y coordinate of the bottom point. Because it's a physical point on the graph, I get a square bracket, and the top y is infinity. The problem that I skipped over, 14, the reason I skipped over it is only one side needed to be extended. We'll get to that right here in a second. So problem 14 that I skipped, you'll see that the left edge has a period. The right edge has a period. The left edge doesn't. So the only thing that needs to be extended is the left part. If the graph had periods on each edge, I wouldn't have to do any extending. But the left edge doesn't have a period, so it needs to be extended. When I extend it, eventually it goes to the far left edge of the x-axis, and slowly but eventually it gets to the top of the y-axis. So left is negative infinity in the x direction, positive infinity is up in the y direction. I've extended this graph the best I can. Now I'm going to write down the domain and the range. I'm taking the most left point in its x, the most right point in its x when I do the domain. So my domain is going to be from negative infinity to 0. Infinities always get round brackets. Points on the graph usually get square brackets. For the range, I'm going to go bottom point in its y, and then top point in its y. The bottom point has a y coordinate of 0. The top point has a y coordinate of infinity. Let me make up some problems outside the handout real quickly here to give you some more practice. So try to find the domain and range of this one. This is the point 3, 2. So I made a graph that one side needs to be extended, the other side doesn't. I wrote a period on this side, so this side doesn't need to be extended. This side does, and I'm assuming the graph is going to keep going up and to the right. So you need to extend it. When you extend it, it goes to the top of the y-axis, to the far right edge of the x-axis, so it goes to a double positive, because the x-axis goes positive to the right, the y-axis goes positive when you go up. So for this problem, if I try to write its domain and range, first I'm going to do the domain. I need the most left point and the most right point and its x's. So the domain here is going to be positive 3 to infinity. For the range, I need the bottom point in its y and the top point in its y. So my range is going to be 2 to infinity. I'll make up 3 more problems and then do the last problem in the section, which is a trick question, and it's not going to make its way onto the test, but it'd be nice if you could get it. So one more, how about this? Let me label some points here. Here's the point -6, +5, -4, +8, -1, +2, and 1, 3. So try to attempt to find the domain and range of that. Pause the video maybe, and then come back when you have it done and check. So this graph doesn't need to be extended anywhere because I have periods at the edges. I have all the endpoints labeled. So for my domain, I'm going to find the most left point and the most right point, and I'm not extending. The domain is going to go from x equal to -6 to x equal to 1. The range, I need the bottom point and its y and the top point in its y, the range is going to go from 2 to 8. So this is from, I don't know if it's the easiest, but it's one of the easiest kinds of problems. Because the points are connected, I know it would be wrong just to write the 4x values and the 4y values for the domain and the range. But the endpoints are perioded, so I don't need to extend my graphs, which makes it, for me, easy. All right, 2 more reviews and we'll do the last problem. So find the domain and range of this. So this graph, if I want to find the domain and range of it, because the points aren't connected, then it'd be wrong to connect the points, and my domain is just going to be the x values, my range is just going to be the y values. So for this graph, the domain's going to be -9, 1, and 6, the x coordinate of the 3 points. Again, it's wrong to connect the points if they're not connected. The range is going to be -4, 1, and 3 in whichever order you want, the y coordinates of the points that are given. All right, one last one. We'll do the last problem in the section here in a minute, but it's not on the test. One last one. Let's do this then. So again, since the points are connected, I need to extend the graph. I need intervals for my answers. It would be wrong just to write -5, +5 for the domain, -5, +3 for the range. And I wrote this point wrong. This is a 0.35. Duh. For this graph, the left edge doesn't need to be extended, but the right edge does. I extend it to the far right edge of the x-axis and to the bottom of the y-axis, which is positive infinity in the x direction, negative infinity in the y direction. Now I try to do my domain. I need the x-coordinate of the most left point and the x-coordinate of the most right point. When I go to write the domain for this, I'm going to say it's -5, the x-coordinate of the left point, to positive infinity, the x-coordinate of my extended most right point. For the range, I need the y-coordinate of the bottom point and the y-coordinate of the corrected top point. The range for this is going to go from -infinity to +3, the x-coordinate of the bottom point. The y-coordinate of the bottom point, the y-coordinate of the top point. Infinities generally get round brackets. Points on the graph usually get square brackets. I'd never make a deal if you don't show the right bracket on the test. I'll probably scribble it in, but I won't take points off. Last problem, absolutely guaranteed not to be on the test, but for what it's worth, we can try it. And again, if you can't figure this out and you want to stop the video now, it's completely fine. It's not going to penalize you at all. It's a trick question. The sister problem to this, which I think is 17, is also a trick question. This graph doesn't have a period, so I need to extend it this way and extend it this way. It's a horizontal line. It eventually goes all the way to the far left edge of the x-axis. But it doesn't go to the top of the y-axis or the bottom of the y-axis. The y just stays 2. So the extension to the left goes to the point -infinity 2. The extension to the right, it goes all the way to the right edge of the x-axis, but it doesn't go up or down. It's just a horizontal line, and the y stay at 2. The domain for this graph, I need the x-coordinate of the most left point and the x-coordinate of the most right point. The domain is going to be negative to positive infinity. It's the range that's screwy, because this point they're all at the same level horizontally. Every single point is equivalently a bottom or a top. This graph doesn't really have a bottom or a top. That's the part that would make this not come on the test. Technically, the range is from 2 to 2 because the y-coordinate of the bottom point is 2 and the y-coordinate of the top point is 2. And you could just say the range is just the number 2 because every point on this graph has a y-coordinate of 2. Again, absolutely never put a horizontal line or a vertical line on a test and expect you to find the domain in the range. Is just something I thought would be interesting to look at. It might be, something that you figured out, and it would be very cool if you figured it out. But if you didn't figure it out and don't understand it, it's not that important. Okay, so that's the end of section 3.2. Hopefully you can dig through all the homework problems, all the odd problems in this section, and do well with those. If you can't rock those problems, then you should come visit me or visit a tutor to make it so you understand those problems before we get too close to a test.